Hello everyone, thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Geometric and Material Nonlinearities, and it is going to provide you the fundamentals of geometric and material nonlinearities, and also the mathematical derivation of Kitchhoff beam and the Timoshenko beam. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the material nonlinear theory and the Kitchhoff and the Timoshenko beams before wrapping up with conclusions. In this video, we will set up a proper description of the statics and kinematics of structural elements subject to large deformations. When we employ the terminology large deformations, it may not be clear what we exactly mean. More accurately, we will say large displacement gradients. In this video, we focus on small strands. The large displacement gradients can be observed in structural behavior, while the strands are smaller than 2%. The only restriction resides in the constitutive relations. That is the relation between stress and strain. In this video, we assume this relation is not linear, and we call it material nonlinearity. The figure of a spring model illustrates the linear and nonlinear responses using a one-dimensional spring device. Assuming that both the length and cross-sectional area of the device are unitary, displacement becomes strain and applied load becomes stress. In the case of linear springs, the strain energy density is a quadratic form of strain, defined as U equal to half of elastic modulus E times epsilon squared, and the stress-strain relation can be defined by differentiating the strain energy density as sigma equal to E times epsilon. In the case of nonlinear springs, the strain energy density is a more complex form than the linear energy equation, and the stress-strain relation becomes nonlinear. The majority of this video is devoted to two-dimensional beam elements. Beam elements for two-dimensional analysis are of interest in their own right, but also have a didactic role. We will start the discussion by departing from an initially flat element, using a degenerated form of the green Lagrange strain tensor. The axial strain can be expressed as epsilon equal to du over dx plus half of dw over dx squared, with ul the axial displacement at the center line, and assuming that plane cross-sections remain plane. The displacement in the x direction is given by u equal to ul minus zl times dw over dx, where zl measured with respect to the center line of the element. Combine these two equations, we have a new expression and a curvature chi. For an initially curved element, the new expression must be modified as epsilon equal to epsilon L plus ZL times chi, with the membrane strain and the W dash. Then the virtual strain follows in a straightforward manner as delta epsilon equal to delta epsilon L plus ZL times delta chi. As in truss elements, the internal virtual work involves only the axial stress and the axial strain. Now we introduce the finite element shape functions. In this part, we assume that the beam is sane and that the Kitchhoff assumption holds. A possible matching interpolation is then a quadratic hierarchical interpolation for UL and a cubic Hermitian interpolation for W, with C the isoperimetric coordinate along the axis, and nodal arrays. According to the Kitchhoff assumption, theta is equal to dw over dx, and delta AC is the relative displacement at the hierarchical midside node C. Differentiation of the shape functions leads to these equations, and we have a new equation to elaborate the original strain equation. assuming a Bubnov-Galergan approach. The virtual displacements are interpolated in the same manner as the displacements, and the expression for the virtual strand attains the discrete format. For the present, we will assume linear elasticity, so that the stress resultants can be integrated to give n equal to E times A times epsilon L, m equal to E times I times chi. Where I is the moment of inertia of the beam, it has been assumed that the strands remain small, so that for the cross-sectional area of the beam, we have A is approximately equal to AO. Substitution of these expressions and the virtual strand into the virtual work expression for the beam, we obtain a new expression of the virtual work. Since this identity must hold for arbitrary delta A and delta W, the following set of equations results this expression, with the internal force vectors. This expression is nonlinear and must be solved using an iterative procedure, such as the Newton-Raphson method. For this purpose, a truncated Taylor series is applied, and the residue is forced to zero, so that the following matrix vector equation results this expression, with the submatrices of the tangential stiffness matrix defined as KAA, KAW, KWW. The last term of KWW can be identified as the geometric contribution to the tangential stiffness matrix. When material nonlinear behavior is to be included in the analysis, such as plasticity or damage, the beam must be divided into a number of layers. In order to be able to monitor the spread of plasticity or damage through the depth of the beam, for most practical purposes, using 5 to 9 Gauss integration points through the depth surfaces. Considering that plasticity and damage can be caused in an incrementally linear relation between the axial stress sigma and the strain epsilon, E tangent is the tangential stiffness modulus which, for a given x, only depends on the position with respect to the center line. Closed-form expressions for the normal force and the bending moment can no longer be derived. Instead, we obtain for the rate of the normal forces and the rate of the bending moment respectively. For a layered beam, the stiffness matrices become new expressions. However, this procedure raises membrane locking. Methods to remove or reduce membrane locking can be put on a more rigorous footing using the Hu-Weshizhou variational principle. This involves the membrane strain epsilon L being replaced by an effective membrane strain epsilon effective. Using a linear interpolation for UL and delta AC equal to 0, we can elaborate this identity for the shape functions. The performance of the Kirchhoff beam element is now demonstrated through the simulation of the bar column of the simply supported slender column shown in this slide. The column has length L equal to 200 and a uniform cross-section with an area A equal to 6 and a moment of inertia I equal to 2. The Young's modulus is E equal to 7.2 times 10 to the 6th power. Both ends of the column are simply supported and the column is loaded by a point load P. The beam has been discretized by 10 Kirchhoff beam elements. The equilibrium path is obtained using Rick's arc length method. In order to trigger the correct buckling mode, a small sinusoidal imperfection has been assumed, with an amplitude edge that varies from 0.001 to 0.1. The buckling load, P critical, at which loss of stability occurs, follows from the classical analytical relation. For the given dimensions and material parameters, P critical equal to 3553. From the graph in this slide, it is observed that all the simulations converge to this buckling load. As an alternative to using the Kirchhoff hypothesis, we can adopt a Timoshenko beam formulation, which includes shear deformation. As a consequence, theta, the rotation of the normal to the center line, becomes an independent variable, and the curvature is given by chi equal to d theta over dx. Then we define the shear force and the virtual work contribution with the shear strain gamma defined as theta plus dw over dx. It must be added to the virtual work equation. The interpretation can be expressed as this equation, and the spatial derivatives follow by straightforward differentiation. Using quadratic hierarchical shape functions for the interpolation of UL, W, and theta gives U equal to HW equal to H theta, with HU as defined in previous, and the nodal variables A, W, and theta from the spatial derivatives and the curvature and the shear strain. We obtain the new expressions for the shear strain and curvature. Substitution of the interpolations into the virtual work, and noting that the discrete nodal variables now consist of the set of A, W, theta, use a new virtual work equation. Since this identity must hold for arbitrary delta A, delta W, delta theta, a set of equations results that has the familiar appearance of the balance of the external and the internal forces, and we have the new internal force vectors. As with the beam based on the Kitchhoff hypothesis, a Newton-Raphson method is used to solve the resulting set of nonlinear algebraic equations, and the linearization process results in this expression, with the submatrices of the tangential stiffness matrix KAA, KAW, KA theta, KWW, KW theta, K theta theta, where the last term of KWW can again be identified as the geometric contribution to the tangential stiffness matrix. The expression J bar can be derived by considering the rate of the shear force, as defined in a new equation, with G tangent, the tangential shear modulus, which depends on the position with respect to the center line. Very acceptable solutions can be obtained when quadratic hierarchic shape functions are used for all variables, in conjunction with a 2-point Gauss integration. However, for slender beams, that is, if the length to thickness ratio becomes high, so-called shear locking can occur. This can be overcome by forcing the shear strain to be effectively constant along the beam axis. By adopting the constraint, and the set of nodal variables becomes new expressions. The performance of the Timoshenko beam element is now demonstrated through the simulation of the frame of a simply supported shown in this slide. The frame has height h equal to 120, and the length b equal to 120. All elements assume uniform cross-section with an area A equal to 6, and a moment of inertia I equal to 2. The Young's modulus is E equal to 7.2 times 10 to the 6th power, and the shear modulus G equal to 5 times 10 to the 6th power. At points 1 and 21 of the frame, they are simply supported, and point 13 is loaded by a point load F. The frame has been discretized by 10 Timoshenko beam elements. The equilibrium path is obtained using Rick's arc length method. The relation between the applied load F and the vertical displacement V of the frame shows in this slide. From conclusions, what we learned: geometric nonlinearity often occurs when deformation is large. Material nonlinearity occurs in the constitutive relation, that is, stress-strain relation. Kitchhoff beam theory assumes that deformed plane sections remain plane under deformation. As an alternative to using the Kitchhoff hypothesis, Timoshenko beam deformation can be adopted to include shear deformation. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative, and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching